So welcome to the AMA Online. Today we are with Anne Patel. She's going to be talking to us about, I've got on student perspectives about data. And I just want to ensure that everyone's got their mics muted so that we can hear Anne clearly. I'll mute my mic very shortly and then we can get underway. If you have any questions, please feel free to just type in the chat and we'll get underway shortly. Perfect. And you can take it away. And I'll keep letting people in.
Okay, can everyone hear me? I'm assuming they can. You can hear me, Sunny?
Yeah.
I just can't see myself, but that's all right. And can you see my screen? I've got the whakatauki here. Ma whiro, ma pango, ki oti ai te mahi.
No, can't see it.
You can't see it?
No, you'll need to share your screen, Anne.
Oh, hold on a minute. Thanks, Marla. I'll share screen. What about now?
Perfect.
Yes, we can see it now.
Okay, great. All right, I might say that again then. Ma whiro, ma pongo, ka oti ai te mahi. And I just want to acknowledge the work of the AMA, particularly Robin Hedefin and Pip Arnold, and getting this wonderful format for us together to share our ideas and our knowledge, and it's wonderful. So I'll quickly go because I think there's only half an hour of talk. So today I really wanted to share with you, I'm coming to the end of 6 years of PhD study in statistics, and I have read some wonderful research in that time, and I just wanted to share with you one particular piece of research that I think every teacher who works with data should know. Just a little bit about me. I grew up in Naumai, Ruawai. This was 40,000 acres of flat land, the Ruawai Flats. But I lived underneath this pretty special mountain, Tokitoka Peak. And I was laughing and thinking it's no wonder that I have such a fascination with distribution because of the way the shape of this mountain is. And from the top of this mountain, you can see this wonderfully right-skewed mountain, or left-skewed, depending on your angle, and looking at the differences and the variations in mountains is fascinating. It still fascinates me today. Right, so I'll get started. We're all about the big ideas. We can't have a curriculum that's a mile wide and an inch thick. We have to focus on the big ideas, and in statistics, Jane Watson and co in Australia have sorted out what are the big ideas for classroom statistics. And as we go through, I know it's great to share, and I'd really like in the chat to have a record of one thing that you have done in your classrooms where you posed a question, or better still, got the kids to pose a question, investigate some phenomena and data, collect some data and analyze that data, and then make some decisions, conclusions, give ideas for action to happen. And I'd like you to think about what that was, and at any point in this thing, just type it down into the chat box. So just give me the context and the question that you were investigating. So I'm going to talk about all of these things and how they look. So you'll all be familiar with the data detective poster in the left-hand point. We're trying to get some more printed. It's a money issue, but more are coming one day. And so we start with a problem. Data statistics is all about starting with a problem. And some schools are on a continuum. Some schools might just have teacher-posed problems. Some schools are fantastic to go in and see that they have themes that run all through the year or through the term where they're investigating through those themes. I've just read a paper recently that said, let's try and turn these investigative questions into inferential questions. And I changed a few of the last ones there. What proportion, the original question was, what fraction of the newspaper are ads? And if you can just change some words in there, I can change it to an inferential question. What proportion of the newspaper tend to be ads? That tend to be, sort of puts in the idea that there's some variation. I'm expecting variation. I don't expect that this week's newspaper will have the same proportion of ads as the next week's. So it sort of puts that idea that I'm expecting variation in everything I do. So variation is all around us. How do we teach with variation? Teaching with variation is the spice of the life. And I always remember Michael Shadbolt's quote, if you're not having fun teaching statistics, you're not doing it right. And I love that. So where we see variation, and what we're looking at here is a display of students' bedtimes. This is one class that I was working with. This is their census at school data. And so we just pop that into a graph. We can see variation. We can see that some students go to bed at 8 o'clock and the latest was 10:30. And we've got variation in between. Now, so when you have variation, you're going to be looking at distribution. And distribution is a really important concept. And there's been lots written about distribution in university textbooks, but there hadn't been a lot written about what does it mean? How do people put it together? How do kids look at it? Until Arthur Becker and Gravamere back in 2004 started looking at it and started saying, well, that it's really a collection of individuals. These are individual data points, but when we put them together and we form a distribution, really, then lots of things appear, like the center, the spread, the density and the skewness. So this is a very simple beginning framework that we stats education researchers started looking at. But really the thing is that they saw that statisticians or people that work with data a lot really saw distribution as a thing, a unity, a thing to be reasoned about with all these things that belong, these properties that belong to it. So why is it important to see distribution as a thing? And really, COVID has bombarded us all with data and graphs and models. And this is a model of infectiousness. And you can see that beautiful distribution occur, but you can't see the individual values, although individual data has led to the creation of this model, but the individuals are gone. They're nowhere to be seen. And all we're left with really is the shape, the outline, and to reason about that shape and the outline, models of infectiousness is saying that we're really infectious between days 2 and 8. That is our critical infection window. And what can we do to stop COVID spreading if you're pre-symptomatic, symptomatic, environmental, and asymptomatic. And so that's how people learn from data and learn about, well, what can we do? What's the best thing to do to stop this thing and get that R naught down below 1 so that it's declining instead of exponentially increasing, going above 1. So why is it important to move students from an individual perspective, which they're obviously going to start at, the individual dots and individual data, to an aggregate view of data? Well, it's really important because all of the inferences and ways of comparing groups and looking at how two variables vary, covariation, are made from aggregate measures, statistics, like the means, the medians, the modes. It's not about individuals. Okay, so that is really, really important, that our job as teachers from year 1, kindergarten, is to shift these kids from an individual to an aggregate view of data distribution. And some other research that came in is that really important is if you're going to think about the aggregate, then you've got to construct it. You, the student, has to construct it. And we've got several ways now of helping you do that. So the first is actual physical manipulatives. You can see there the dinosaurs, and little kids can say we've got more fish than elephants on this graph that we've made. And that's a fantastic way at year 1 to be looking at data, ordering data, classifying data. The scatter plot, I couldn't find a data card with just a normal distribution. I just had the scatter plot one. But Students' abilities to draw graphs lag far behind their ability to interpret graphs and interpret data. And for that reason, those manipulatives and data cards are really, really important. Please, if you're a primary school teacher, make up a set of data cards and a secondary teacher. Go on to Census at School, have a look at some of the data cards that are there. You can do an advanced search on data cards, get a set of data cards, create your own, whatever context you're exploring, create your own cat data cards or Pokemon data cards, dragon data cards, whatever it is, create your own and have them there and share them with your colleagues. Here's my data set, here's my data cards, can I have yours? Whatever themes you're working on. That's Anna Ferguson's data card down below. And those are made up from Census at School data, but also names. They're given names like Rita, and that's from the marathon data, that we'll call marathon data, which is pretty cool. Thanks, Anna. Over on the top here, we've got hand-drawn, top left, top right, we've got hand-drawn graphs. Really can't stress the importance of students constructing their own graphs. And a lot of the research is saying, don't be fussed if it's not a graph that you don't recognise as a teacher. Just let them construct their own graphs, their own representations, and compare and contrast with their friends what they've drawn and see which representation unclouds their mind about what the data is saying, or whether it's not quite there, it's not telling all the stories that the data's got to tell. And the last thing we've got is technology, which is just fantastic. You've got loads out there, Fathom, Tinkerplots. I'd highly recommend Tinkerplots for primary school students. It is fantastic. It has been designed by stats education researchers who know how children think about data, and it is intuitive and it is designed to be intuitive. So down there you've got categorical data in bins of where the kids eat their dinner, and this is my class that I was looking at. So you can see that, I'll just move this out of the way. You can see that most of them eat their dinner at the table, which is great. A few don't, but eat out or eat on the couch or in front of the TV or computer. Okay, so there are some ways we can get students to engage with data, but this is really the crux of what I'd like to share with you. How do students perceive data? And according to Konold, Higgins, Russell and Kahlil, they see data with different lenses on. It's like they've got glasses on when they're looking at data. So the first way they can think before they even look at the individual dot is as a pointer to the larger event or context from which the data came. And I'll give you an example in a minute. Then they can shift to a case value, and those two are sort of interchangeable. They go together, but we can distinguish between them. Then they go to a classifier view, which is looking at a group or a frequency of values. And finally, they may or may not shift to an aggregate view where they perceive the distribution as a whole with these various features. Okay, so here's an example for year one students that were asked their favourite colours. So you can see, you can chuck it into Tinkerplots with a collection, you can graph that into bins. And so how a student might see this representation, this graph down here, they might see it as, well, we told our favourite colours to the teacher. They might see it as Juan likes red, Anne likes blue. Blue is my favourite colour. Students love to see themselves and others in the data, and that is a really key idea of looking at graphs. Where am I? Where do I belong? Where am I in relation to the group? And when they come to see aggregate in a very simple context like this, they might start to aggregate features and say half of the group likes red. Okay, so that's a very simple explanation of that. In their paper, they also asked the students the number of years that they had lived in the town. So I just thought I would put this information into Tinker plots, and you'll see that top left, it comes out as just random collections. It's just a random screenshot plot. When you start to drag them to the left, they'll start to put it into groups or bins, and you can see that it's split, and you can say, oh, look at that. There's quite a few between 0 and 20 years. And you move to the bottom right, and it will spread it out even more. And you start to see the distribution forming. You can see in that bottom left one, it's quite skewed. It's like on a triangle like that. And when we go even further, we can stretch it out totally. We can see the full variation, the full spread. And these are fantastic interactive plots. The kids love playing with them. And so one of the pointer views that kids might see is they say, well, I didn't know how long, so I had to go home and ask my parents, how long have we lived in this town? A case value view would be, oh, look, I'm focusing on the maximum. 37 years is the longest a family has lived in our town. Classifier, 4 families, so we might be looking at the modal value there. 4 families have lived in the town for 3 years. And aggregate, we're looking at the whole thing, and we're really using proportional reasoning skills. About half of the families have lived in the town for less than 10 years. And that word about implies there's some uncertainty in that claim. About half of the families have lived for 10 years. So in year 9, we're looking at box and whisker plots, which can be superimposed over the individual values. And I wish I'd read this paper before I did my master's in 2008, because we'd done everything right. We'd had a 6-week statistics course, and I was asking a young girl about what she saw in this plot, this box and whisker plot. And she said to me at the end, she got really frustrated, and she said, it's just a bunch of lines to me, miss. And I realised then that that is actually what she saw. The abstraction, the level of abstraction in that graph was too high for her. She lost the individual. She hadn't had enough experience with the individuals and the density and the clustering and the shape to really have a good grasp on what that box and whisker plot meant. So you can see some of the tools in here that the kids can play with. You can see the modal value, the green line, the mean and the median, and the hat plot superimposed. And the lesson for teachers is don't lose the dots. The dots are really, really important, because we're not saying here, this paper is really clear and not saying that an aggregate view is the pinnacle of where you want to get to. In fact, expert statisticians go between the 2 views of individual case values and aggregate, and everything in between, depending on the questions they're asking of the data, depending on what they want to know, and depending on the further investigations that they want to find out about. So the problem is that what we've found in research is that some students are inclined to view data from only one point, and that has implications for the whole investigative cycle. If they only see data as individuals, then they're going to struggle to use the average, to compare groups using the average and any conclusions they draw from data. Okay, so what can we do about it? Well, I've been doing some work with my school, because I've got little kids at the moment, and I went into my little girl's class, Vivi there, standing in front of the graph, how many things are in the lost property, and I was so chuffed. I took a photo of this and I said, this is great statistics. Year 1, this is fantastic. Thank you so much for doing it. And I asked a bit about the lesson, and basically they got the lost property and they dumped it on the floor, and then they had the students individually lay out those stuff that was in there. And also, really importantly, they predicted, they said, what do you think is the most in this box? What object do you think has got the most number of things in this box? And of course, the students who went past it every day said, well, it's got to be jerseys. And it turns out that this is maybe their first time where data dissolves their preconceived ideas. And in fact, all of those stinky little socks buried at the bottom they had more socks than jerseys. And that is really, for me, the first data as evidence, doing some investigation, changing your opinion about what you think is happening. And also I read a fantastic book called Teaching Statistics at its Best. It was an oldie but a goodie, and it told me that those orange squares and yellow squares are pretty abstract for year ones, and perhaps it would be better to scaffold them through using icons, using pictures of t-shirts to draw a graph. So the next year we did it with icons and pictographs, which is really important to establish an individual view. This is from Census at School. I encourage you all to sign up to the census, do the census with your class, and then go and explore the data in Insight and Census at School. To me, this isn't much of a distribution, but what I love is the variation. When I saw this graph, I thought, wow, what's going on here? We've got, where did you eat dinner? At the airport, at McDonald's, fantastic. At a friend's place. But the one that really got me was at hospital with Dad, and that really brought a personal dimension and a variation. And one thing that's really struck me about data is, and analysing data, is that ability to imagine yourself in someone else's place. And you might eat your dinner at the table every night, but some nights you might have to eat it at the hospital with your dad who's sick. And also just to look at how these could be classified, you know, quite a few of them could be put into the table scenario. And then that also brings up the idea of the investigative process. How are we going to collect the data? Can we rely on the data? Is it reliable? Is it classified right? And some really, really cool ideas about the whole investigative cycle. So individuals vary, and we have to account for that. And I think this graph just says a lot about individuals varying. The next thing I'd like to share with you is hot off the press. It's from Katie Makar in Australia. She's a wonderful stats education researcher, and she's gone into classrooms and done 2 loopy airplanes. And I've never seen loopy airplanes before. I've seen paper airplanes, and I've done orbital express before, which is just screwing up 2 different pieces of paper and seeing how far they land away from the target. But I love this, loopy airplanes. And when they did some data analysis, you can see straight away using technology that the distance there on the vertical axis, the green ones are going to fly the furthest. So I'd encourage you to read the whole paper. I can send it to you if you want it. So the design cycle, they had to do iterations, they had to test, they changed things around, they changed the width of the loops, they changed the lengths, they changed the location. I think the S stands for split, where they split the location, the middle and the ends. But you can see there, we're looking at distributions, we're looking at variation, and we're looking at trying to make a conclusion to say which of these is the best, which will fly the furthest. So that's about design. Another context you can look at is repeated measures. This is part of my PhD, so if you've seen this before, you just have to bear with me. So basically what we did is we got a moon hopper here. Sorry, the dog bit it, so it's a bit floppy, but we asked all of the kids to repeatedly measure this moon hopper, and we gave them a tape, and you can see that it's quite difficult position like this. And those kids, they also measured the handle electronic calipers, so 2 different measurement devices. They then put the circumference of the moon hopper in the light blue post-it notes, the handle diameter in the purple, and they then put that on the board, and we had a half-hour conversation about the variation that they saw. Now the idea with this is there is one true circumference, but it's unknown. You will never know what it is. True but unknown circumference. But our data can tell us or indicate what that true but unknown value is. It's called the signal in the data. It's the center. You can see the boys are starting to put up variation there. but they could tell me that the centre is going to be about 114.5 centimetres. So it also highlights kids that can't measure, so because we did get an outlier of 80 centimetres. So that's called repeated measures, and I just pop that in as an extra station on the census at school stations when you set that up. And then you can talk about one of these stations wasn't like the others, and really get that idea that all of the census at school stations is about measuring different individuals. But this one station is many individuals measuring one object, which is a really awesome context to talk about. And when I did this with the teacher, guys, can you be quiet, go or pop out, please? So my teacher said once she got the idea of repeated measures, she saw it coming up everywhere in her curriculum. And she said she was an orienteer and they had the cross country around the school. And so basically I looked at my old college and said, yeah, I used to run around the field. Well, how far would that be? And when you get the kids to do that using technology, it'll be similar, but there will be variation. And you can have a look at that variation and talk about the causes for that, what caused that variation that they can see and the differences. And another context, another measurement context, which is, I love measurement, is this idea of process measures. So it's more like a manufacturing context, making something to a fixed criteria. So you'll see Konold and Harradine used a Play-Doh extruder and they made fruit sausages. And they said, you've got to make them 5 centimetres long. And so there's the different groups of kids making these Play-Doh sausages or fruit sausages. And you can always rely on variation. Variation will be there. As hard as you try and get those things exact, there is going to be variation. And again, you'll get a signal when you weigh them or measure them. And the signal will be the centre, and the variation will be, the noise will be the spread away from the centre. I was thinking about doing this as 3D design. I know schools have 3D printers now, and thinking about consistency and then creating a design, looking at the consistency of the product that it produces, perhaps, something like that to bring data into design. And I got this idea because my littlest 5-year-old, we watch videos of manufacturing processes, pretzels, bread, string. They're really interesting on YouTube. And my 5-year-old asked me the other day, Mummy, how do they make pins? And I actually haven't yet got a video to do that. It's really, really interesting. The variation is very small, but there will be variation. Okay. Another context for looking at data is, and another idea that teachers need to bring in, and this is coming into intermediate and secondary schools, is this idea of sample to population. I'm taking a snapshot. I'm looking at, this was from Census at School, students' bullying experience. Year 7, when did they get bullied? So they could say never, preschool, year 1 up to 7. And this is what this class result data showed, that 5 out of 32 had never been bullied. That's not good. But really, when we're talking about the investigation cycle, Konold and et al. Really stress that the perspective you should take on data should serve your questions rather than the other way around. Don't try and force a question and then try and make kids look at aggregate shapes. That won't work. We actually have to start with the question, get the right data, analyse that data, and then form some conclusions. So if you keep in mind that snapshot of a sample of one class, one intermediate year 7 class, then you can go into Census at School, you can look at the whole distribution, the population, 32,000 students. Actually, that's not right. This is a random sample of 1,000 year 7 Auckland students. So we're trying to compare apples with apples. But I've got 1,000 students here. You can see that about 12-13%, which is similar to what happened back in the sample. But what is not similar to what back in the sample is the preschool. Here we have quite a lot getting bullied in preschool. In the overall population, not so much. It's more systematic. So then they might suggest reasons for that. They might notice there's a difference. There might not be a difference in your snapshot. But we're always thinking about this relationship between sample to population, so we can make inferences about some wider universe, about the bullying experiences of all Year 7 students. Flipping that round, there's another context where we can know about the population. We can never know about the population here. We can never know about it. This isn't all of the Year 7s in New Zealand. It's a sample, but it's telling us something. So flipping that round, we can know some theoretical populations, and this is really about reconnecting chance and data. So the investigative question you might pose is, what is the best card for winning additional bingo? And again, this comes from Katie McCarr. Basically, I hadn't seen this before, so I hope this is new for some of you. Set up a 5x5 grid, paper 3 + 8 on it. So you're pulling it out of a hat. You've got all the numbers 1 to 10. So you're going to have 100 cards in a hat, and the winner is, kids have to mark it. So I might put a 3 in the first corner and a 10 in the last corner. They have to mark off all their numbers. Really, really important. Her paper is called Predict, and it is super important before you start collecting your data that you do a prediction. So you can see here, she must have had a lot of students doing predictions, but you can see that some predicted that they'd get 100. Maybe they got confused. Maybe they didn't understand the game addition bingo. Maybe they thought it was timesing. Two kids have said, I'm going to get a 1. I predict 1's going to be the luckiest number. I don't think so. But then, really important, let them play the game. Let them create their own representation. So you see that lovely circle representation. Doesn't mean a lot to me, but it will mean something to those students. And this little list down here on the left, not sure what that means, but it will mean something to those students. There will be some deep thought processes going on as they collect that data and try and represent it. The graph here, our empirical data, that's more along the lines, more normative as to what you and I would be expecting, but not all kids are going to think like that. And that kid, whoever's doing that, is having a great go at aggregate reasoning. Okay, so comparing experimental with theoretical distributions is a really important aspect of data. When they were asked, which card do you think is going to be more likely? One student said they're all highly likely, the 10s, the 11s, the 12s. And then they went into some formal data analysis, and they probably went back and compared and contested and said, which of these best shows what we want to see here? And that's really important, that students compare and contest their representations of data so that they can all agree that something triangular like that is forming in our minds. And I went into Excel. I love spreadsheets, and I did this up, and then Excel must have changed or upgraded, because it says, would you like some ideas? And I said, sure, let's have some ideas for how to represent this data. And it came up with this funnel chart, which I'd never seen before. And then I finally got this chart down the bottom, which I thought was more representative. So really important that let them play with Excel. What a fantastic opportunity to go into Excel. I'll go fast because I'm running out of time, but statistics in service to other subjects. We don't have a lot of time to draw graphs in our subject. Let's give it to the PE teachers. I went to a PE teacher for my master's, and I said, I want to see how your kids draw graphs in PE. And let's see if any of the learning they're doing in statistics is transferred over to your PE class. So I asked the question, which is the best predictor of faster freestyle speeds? Is it kicking or arm movement? We got them to do a length kicking only with a flutterboard in front, arm movement with a flutterboard on their feet, and then a full length of just normal freestyle as fast as they could. And these are the graphs or representations that the students came back with. You can see that this girl here, and I wish I had known the individual view now, has a really good individual view, and she wanted to draw a line because she knew that she had to connect the dots somehow. But arms faster was really going off her personal experience. It wasn't sort of anything to do with looking at that data. This group here, they didn't draw a graph, they just did averages. They must have seen me sitting down the back of the class. The group down in the bottom left, they interestingly took the top 5 fastest speeds and found an average. Took the bottom slowest speeds for arms and legs and did the average, and then plotted that, which is really, really interesting. There was a girl I interviewed, she wasn't there on the day, but she said to me, I'd put the students along the bottom and I'd put their times along the top and I'd connect it. And initially I thought, where is she going with this? But actually, if she had put the total swimming lengths on as well and not joined them going horizontally, actually looked at, maybe coloured the proportions, that would have been a wonderful way of seeing that the students that had a good kicking speed were faster. And then you've got the kids that are seeing distribution as aggregate and can abstract from the individual data points, although this group didn't put it on the same axis, and this group down the bottom did a good thing by putting it all on the same axis so they could compare. Some really cool things for starters or end of lesson, if you've got 5 minutes, do a prediction. Have I got the pointer here? Yep. So I love this pointer. You can see predict the ages of all the people in our school, a lot of young kids, some young teachers, and then quite a few older teachers. Then we come to baby names. There's a spike at Mike. So now we're really looking at aggregate views of data. I love Baby Wizard, it's fantastic. You've seen my little daughter, my 7-year-old, I wanted to call her a female name, one that wouldn't get confused. You can see she was classically named in the 20s and now we've taken off, but there's still only, I think it's 350 per million. But then I discovered, if I just typed in Viv, that, I don't know if you can see that because my thing's in the way, I'll put it over here, that Vivian was in fact a boy's name as well. Who knew? I should have probably known that. But if you look at boys and girls together up here, you've got 2,800 kids called Viv. So it was quite a common name, and I thought it was uncommon. Who knew? Nico's my niece. She's very new to the scene, probably something to do with the Velvet Underground. That's taking off. Look at the distribution, taking off in popularity. Elaine, my second daughter, much more normal. Get the joke. Much more normally distributed. But I'm looking down here and seeing some little shakes here, and I'm thinking, you know what? There's a lot of people like me that are calling their daughters Elaine after their grandmothers. And that's I'll wrap it up there because I'm probably out of time. Takeaway ideas, students' perspectives evolve, and if they don't have enough experience with manipulatives, data cards, technology, drawing their own graphs, then they're probably never going to get to an aggregate view. We've got lots of adults that can't look at distribution as aggregate. In order to understand the aggregate, it must be constructed. Therefore, you must give these students opportunity to do all of these things. Measurement contexts are fantastic. Design and art, get some data analysis going in there. Science and social studies, and PE, farm your graphs out to other teachers, pair up with another teacher. That's your challenge for term 1 next year. Pair up with another teacher and say, oh, in history, I want to know for me how many Māori died at Parihaka, how many British died at Parihaka. I really want to get into that, into data, and really have a really good look at that. Don't remove the dots, even for university students. Individual views are as powerful, if not more powerful, than aggregate views as well. And investigate, do something with the graph. This lovely book here said, don't just do a graph, do something with it. Take it to your principal, stick it in the foyer and say, we've investigated a stream quality. Now we want to do something about it. This is evidence. We've got evidence. We've got to do something about it. I'll end there. I'm a little bit over time. Thanks for staying with me. Sunny?
Thank you, Anne. I think there was a question or two, and I'll just open the floor to see if anyone's got any questions. I think Claire from Palmerston North had a question. Claire?
I was asking if it was important to have them physically draw, or could they do digitally created graphs, which is better?
Both at appropriate times, depending on what you're investigating. I think the technology, that Tinkerplot's technology, I can't sell that enough. It really is fantastic. It's been designed specifically to encourage students' graphical thinking. But it is really, really important that they construct their own representations as well. It's both, it's not one or the other. And I think you can introduce technology really early, actually. I'd be putting, because kids are great, they want to break it, they want to see what they're going to, how can I break this technology? And the graphs they come up with are fantastic, and they will reason with them. And that is your opportunity to say, what can you say, what story is this data telling you? And what's it not telling you? Come and have a look at Charlie's graph. You know, there's some contesting and comparing representations is really important in the technology world, and the physical hand-drawn graphs, really, really important. Yeah, I just don't think we do it enough. And I'd really like primary schools teachers to do it a lot. Yeah, because we just don't have time in the secondary curriculum, really. But my experience, secondary kids still need it. They really need to draw their own representations and reason about them. Yeah. Did that answer that question?
Yes,
Do both and do it lots.
Thank you, Claire, for your question. Thank you, Anne. Everyone, thank you so much.